Okay, so in this course, so in the second unit, that is magnetostatics, we have seen so far now two laws. One is Biot-Savart law, another one is Ampere's law. So in this, from this two, we can actually calculate the magnetic field due to the current flow in a particular structure. Also, if we calculate the magnetic field, we can calculate if we calculate the magnetic field over a region or the one which is excited out of the structure, then we can calculate the current or current density which is flowing inside the structure. So both the way we can easily evaluate that. So this is a very useful concept while you go towards some of the important applications of electromagnetics. Almost whatever that you see, the so-called electrical and electronics, all can be comes under the applications of electromagnetic field theory, starting from motor, plug, wire, and laptop or whatever it is. So everything is actually at nanoscale level to macro scale level. They all actually characterized, we can easily characterized within the classical theory of electromagnetics itself. In some crucial applications, we need to go with the so-called quantum theory. So other than that, 90% of the um, uh, structures can be numerically solved with the this electromagnetic field theory. So that is why actually we have to study this with a very sincere manner. And so I also discussed about the CAT one, and we already discussed about the quiz one. The quiz one will be conducted again on Saturday, that is 4th at 10 a.m. And this will be completely numerical problems from Biot-Savart law and Ampere's law. So you will be given with 4 questions, and you will be attending 3 questions out of that. So this 3 questions will be mapped for 20 marks, and this mark will be converted to 10 marks for the evaluation for your internal marks. I hope you can you just study these two laws properly and relevant numerical problems, and you also see so many numerical problems available in the internet. And so I will be giving a little bit tricky ones since you have only uh, limited portions here. Okay. So we already discussed about the key component of magnetostatics. So how this magnetic field is created. The very important thing we have to learn, or you have to always memorize, always you have to remember whenever you take this particular course into account. So the very first thing is static charge, or the charge which is actually not at all moving, which will simply produce only the electric field. But the charge which actually moving in a particular velocity can produce the magnetic field. So this is the major important difference between the electric and magnetic fields, or we can say the source of the magnetic and electric forces. Okay, so so if there is no movement, then obviously the so-called the velocity in a particular direction, or for an atom which has the electron which is spinning in a particular angular velocity. So this actually it cannot produce the magnetic field. So that is what we have learned from all the two important laws, that is Biot-Savart law and the Ampere's law. So Biot-Savart law tells from one particular angle. In other words, we can say that it is actually telling in the angle from in aspects of the source. The source is nothing but a particular structure which is carrying a current. That current depends on the structure. We have 3 types. One is line, another one is surface, another one is volumetric. Okay, so depends on that, we will get different uh, current behaviors. And whenever we have this different types of currents, then we have to treat them in different way. So that is what actually we are learning out of the numerical problems, that if it is a line vector, better to take cylindrical coordinate. If it is a surface one, it is better to take the rectangle coordinate system. If it is volumetric integration, then depends on the shape. For example, here this volume is completely cylindrical one, so cylindrical coordinate system is. But in case of if it is a more spherical one, then we can go with spherical. Or if it is more about only point charge or something, then we can go with the spherical itself. So depends on the application or depends on the shape of the structure what we have taken into account. We have to apply the coordinate system and corresponding so-called mm, the vector calculus supposed to be taken. So you're supposed to be good at choosing the proper coordinate system and corresponding vector calculus as well as differential calculus you have to apply. So once you have chosen that, you have succeeded about more than 50%. Then remaining are pure mathematics. So you can easily work out and do it. So okay, so this Biot-Savart law tells about if there is a current traveling in a particular direction, and that direction we can call it as AL. Okay, that I can say that the unit of the line vector, and in perpendicular to that, or in a particular point, we have a we supposed to calculate the magnetic field, and for that we are going to draw a line joining between them. So this line joining has a particular angle. So we need not worry about this particular angle as of now. So we have a line vector. So that is nothing but R vector. So this has a unit vector of AR vector. Now, what is the direction of the magnetic field? So this is a very important point. Biot-Savart law is trying to explain that. So it tells about the direction of the magnetic field. Most probably, if it is a line vector, it will be going around. So therefore, it will be going perpendicular to both the line vector, which is carrying the current, and the line joining vector between the point P and the line vector itself. So that is AR vector. So we can easily calculate that the magnetic field, the magnetic fields vector will be perpendicular to both the vectors. So which we can represent as the magnetic field direction will be perpendicular to both this AL vector and this AR vector. And therefore, this two multiplication can only be, these two vectors can only done by with the cross product. So this is how actually it is formulated. It is not like they have derived this so and like that. So this is actually, this is how it is being worked out. And therefore, we can say that this AL vector cross this AR vector obviously will give this the magnetic field direction itself. So this is the very key important point you're supposed to note down, because whenever you told to calculate the magnetic field at a particular point due to the given structure, then first you have to calculate this dl or whatever the structure. If it is a surface, then here it will become k ds will come. So you have to calculate that particular vector, then this r vector. So once you have calculated, this denominator is very easy, 4 pi, you know that this magnitude of the r can be calculated from this r vector. So it is very important to calculate this two vectors. So this dl vector and then this r vector. So these two, if you calculate, then the problem is very much it is solved. So before that, we have to choose the right coordinate system, and that is what we are seeing in multiple cases. Another very important thing, what we have to, what we can use in terms of the direction of the magnetic field, we can use the right hand rule. Okay, so I am always drawing this right hand rule like this. There is a thumb, and we have the fingers like this. So you can also use your own methods. Actually, one of my friend used this method like this. So you can also use any method, whatever that you like. So by this, you can easily understand that in what direction the magnetic. So assume that the line vector is lying on the x-axis. So you can easily understand that it is going to be like that. Okay. And if the current is flowing in the opposite direction of minus x, then it will be flowing in the opposite direction. So you can easily get the understanding, and in a particular point where you want. But in other words, if the line vector is somewhere else in the direction of x and y, then again we can draw the proper the magnetic field, how it is actually flowing in. Okay. So these all decisions can be taken by drawing properly, as well as applying your thumb rules or the right hand rule, whatever it is. So you have to apply that, and you will easily get the you can visualize the magnetic field. Once you have visualized, answer will come naturally. So this is a numeric problem as well as some very important one. And using this, we can do many exercise in the future applications. Like I already told about whenever we discuss about antennas and as well as whenever we work on particular transmission lines, everywhere actually we always take line vectors, and in that, if the charge is moving in a particular velocity, that is current, and then what will be the electric and magnetic field induced out of that. And whenever you connect a, let's say you have a telephone, and this telephone is connected to a telephone cable. The cable is nothing but a line vector. So how this so-called the current or the voltage which is exciting the transmission line, how this wire is carrying the information for such a long distance without any problem, of like change in the frequency all the way. So that is what we are going to see in the transmission line. So that is the second part of this course. So this example we already have seen. So I believe I can skip this part. And this example also we have seen, I think 2 times we have seen. This one, you can clearly see that how to present the answer for a given problem. So it is very nicely portrayed here. So you can follow the very similar method for your exam purpose. As I already told, the substitution method is very important. I am telling again and again because I told this to your seniors, but they haven't done it. And obviously there will be sequential mistakes will come. That mistake will follow because you know about the mathematics. If you do mistake here, everything will follow. And so in case of answer, what I generally see in the answer is how this vector is defined and how this unit is defined. I will come to the value at last, because this value there will be a definite difference will be there person to person. Actually, even I used to tell this particular example that Einstein, when he was writing one of the very important paper of his life, that is called gravitational lens, he forgot to divide by 2, and because of that, when this sun is deflecting the light, it's supposed to come to earth. So this angle actually he is supposed to have this particular constant divided by 2, but he forgot to do that. Because of that, it will become twice of that. So the people will be telling the theory will be wrong. So his career would have been completely lost. So even for such a genius, such a mistake is uh, mm, such a mistake he has done. So that is not the problem. But this particular entire framework is very important. That framework actually what I would like to see in your answer sheet. So for that only I can give marks. Okay. And this particular example we already have seen. So I believe you got it. And whenever you have a doubt, you can definitely ask. Okay. Um, yeah. One particular student asked a doubt about this particular problem. Let me summarize here. So we have a current loop here, and in this particular side, we have to calculate the magnetic field for that. So how to do that? So for this, we have the if there is a current traveling in a particular line from point A to B, at a particular point we have to calculate. So for this, if we make the angles, this alpha 1 and alpha 2, and then what about the current? So here the interesting thing is this alpha 1 and alpha 2 very easily can be calculated. Therefore, cos alpha 2, cos alpha 1 can be easily calculated. Rho most probably no, and I will be given to you. So this magnitude part is very easy. But how to calculate this phi? Okay, so the easiest answer is we can draw here that there are 3 axes, x, y, z axis, and the line is actually traveling in this direction. So this particular point and this particular point, let's say this is point A, this is point B, and this is nothing but 1, 1, 0, and this is 0, 0, 0. So therefore, this line vector I will say this is a line vector. So the line vector is nothing but 1 minus 0, which means 1 minus 0, 1 minus 0, 0 minus 0. So which will give us 1 minus 0 ax vector plus 1 minus 0 ay vector plus 0 minus 0 az vector. So this will give this L vector as ax plus ay vector. That's all. And we have to calculate the AL vectors unit vector. So that is very easy. We have to take the magnitude, divide by that. So you will get ax vector plus ay vector divided by root 2. Now, and this is the vector which actually takes the line joining. So where this AR vector will be coming. So this AR vector is nothing but AZ vector. So this AR vector is going to be AZ vector. Now the magnetic field, the direction of the magnetic field A phi supposed to be calculated perpendicular to these two. Okay, so how to calculate this two? The question is how we can easily calculate. So the easiest answer is the one perpendicular to this AZ vector supposed to be available only in the XY axis. So that is very clear about that. And the second clue is that we can apply the right hand rule. So we can draw the thumb and the fingers. So the magnetic field is supposed to flow in this particular direction. So at this particular point P, this is actually going to flow in this direction. So you can see that this is the direction of the y vector, and in this direction when it is going, it will be minus y, that is minus ay vector. So that is what the answer which we have seen for this particular problem. But in case of this particular problem, we have to calculate the perpendicular one to this. So perpendicular to this one such a way that it will, so it is very easy that it is supposed to be in this direction or in this direction. So we can take any way, like minus ax plus ay vector divided by root 2, or ax, let me erase that. So you have two options. The first option is minus ax plus ay by root 2. Another one is ax minus ay vector divided by root 2. So out of this, which one supposed to be there? The answer can be solved by the right hand rule. The right hand rule says that it is always be in the clockwise direction. So in that case, so we will get, this is the answer. So this is the unit vector. So this unit vector is supposed to be placed. By substituting that, you will get this answer will. Okay. So here I have, what mistake I have done is I have taken both negative. So this will be positive. Okay. So this ax vector will get the positive and ay vector will get negative. So this will be obviously perpendicular to both al vector as well as az vector. So you can also multiply that, you can cross check. When you multiply that, when you take the dot product of this two vector, obviously it becomes 0. So by this we can easily get it. So the next one, what we have seen is the Ampere's law. So the Ampere's law states that the enclosing with the enclosed loop, if you calculate the magnetic field, then you can calculate the total total current what is flowing through the particular structure, so that you can easily do it. So the first example which we have seen is the magnetic field due to the infinite line. So the very important thing, as I already told, first you have to choose the coordinate system, then you can apply the then you naturally you can calculate the then you have to define what is this magnetic field, how it look like, then you have to define this DL. Then when you integrate that, obviously will form. So here we can see that we have to calculate just around the uh, uh, just around at any particular point. Point P can be anywhere else. Okay, so at this particular point, if I want to calculate that, then I can use the cylindrical coordinate system. So with the cylindrical coordinate system, then hereafter we have to define everything. So there are three vectors for a magnetic field. It could be one is along the rho direction, this A rho vector. Another one is along the Z direction, AZ vector. Another one is along the phi direction, that is A phi vector. So these are the possible vectors for a magnetic field. But we are very well know that if we apply the rule of right hand rule, sorry, we have to do like this. So according to the right hand rule, then it will always flow in this particular direction. And since it is an infinite one, then obviously this A rho vector and AC vector naturally will not be available. And therefore, the only perpendicular vector to both this line joining A rho vector and this Z vector is supposed to be A phi vector. So A phi component alone going to be there. So to capture all these A phi vector, we are choosing a circle as the Amperian path. So this drawing of Amperian path is very important. So this decision I am taking from the knowledge of the direction of the magnetic field. Since I concluded that only phi component is going to be available, then I am choosing accordingly. So once that is done, I am drawing the Amperian path. Then for this Amperian path, I have to take the DL. So I have to take a small portion. That DL can be calculated as rho into d phi. Okay, so into A phi vector. Now it is very simple. We are going to multiply this two. You will get A phi vector rho d phi vector. So when you integrate over that, you can take out the constant terms and you will get that. So by this, from this, we can easily calculate that. So this is the easiest way we can do it. Let us so let us do the same thing for an infinite sheet. Okay, so if we take an infinite sheet, let's say that the sheet is available along the x and y axis, and we supposed to calculate the magnetic field at any particular point. Okay, always we supposed to remember it is an infinite sheet. So for an infinite sheet, we could always say that the infinite means origin should not be available, or in other words, origin is everywhere. So I can take any arbitrary point. So first I am choosing the origin point where 0, 0, 0 is defined. Then I am drawing the axis. Then I am placing the infinite sheet. Okay. And in this infinite sheet, due to this infinite sheet, I have to calculate the magnetic field at a particular point P. So that is my objective. That is x, y, z at any particular point. Now, in order to understand the with respect to the line of symmetry, I can cancel out some of the expected directions, so that I will get only one or two directions for a magnetic field. So I have to draw the Amperian path to capture that components. That's all I have to do. So for instance, the current is actually traveling along the y direction. Okay, so the current is actually traveling in the y direction. So let me call it as a ky. That is nothing but current in the y direction. In that case, if I take only two filaments, okay, filament means a thin region, nearly 0-bit region. So thin region, and due to this, the magnetic field, whenever it is traveling. So with respect to this 2 points, when I take the magnetic field along this particular direction, then some of the terms will be cancelled. So what are the terms will be cancelled? We know that we have to apply the rule of the thumb rule that so only two components could be available. One is along the z direction, another one is along the x direction. Okay, so due to one particular, both are in the same direction. So obviously, due to this one, the magnetic field will be available in this direction, and due to this two filament also, it will be available in the same direction. But what about this z direction? It will not be available because that is the line joining vector. So obviously only one component will be available, that is only the x direction. So we can easily say that only the H component alone will be available. So to capture the H component, all the H component, we can estimate the magnetic field at the particular point. So for this, there are two possible x directions. One is above the sheet, another one is below the sheet. Okay, so above the sheet, we will be having this particular direction, that is along the x direction. Below the sheet, it will be going in the minus x direction. So that is what it is described here. So above the infinite sheet, we will be having magnetic field along the x direction, and in the below we will be having, and this H naught value still it is unknown. It is the magnitude of the magnetic field, so that is still unknown. So how to estimate that? For this, we have to draw the Amperian path properly. So how to draw the Amperian path such a way that I can calculate all the x components. So for this, for the very first thing we have to do is we have to mark the point P. Okay, so I am going to take, let's say this is the sheet, infinite sheet. Then at a particular point, I have to calculate so the point P is just now it is in the above the sheet. So only I can calculate this component alone. And in order to calculate for the point P in the bottom, I can calculate for the positive case and I can just put the negative term alone. That is what I can easily do that. Okay. And at this particular point, only this H component alone available. Sorry, the H X component alone is available. So how, in order to do that, I am going to draw, I have to draw the loop. Okay, so this loop is a straight line and it has to be closed. So I am closing this by drawing this. Okay. So this size can be chosen in our own way. So I am taking this length maybe A and this height maybe B, like that. So here it is taken opposite way. So let me correct that. This is B, this is A, like that it is taken. So you should remember this is Z direction, this is the X direction. So a loop is placed at a arbitrary point, anywhere else we can place it. So at that particular point, just above A by 2, we have this point P. Below A by 2, we have point P in the below. Okay, both are going to have the same magnitude. The magnitude is same, but only the direction is different. So how to? So this is one way of drawing. Now you can argue that why I can go for same as that of this line vector. I can go for a circular one. So if you draw circular one like this, then the question of cancelling all the points. So the point actually is keep on varying. And with respect to line of symmetry, it will become a troublesome problem. So that's all. Okay. The next option is, can we choose any other triangle or something else? That is up to you. But you're supposed to find the easiest method to get this all this x component. So it is very well we can understand that it is by means of drawing lines, the loop with lines. So the easiest one is the square one. You can also draw a rectangle. Here we have drawn rectangle only. A is not equal to B. So otherwise you can choose A equal to B, whatever it is. So you can also choose the square loop, but let it be more rectangular one. After finishing that, now I have to say this is the x component. The x component will not be available along the z axis. So obviously those integrations will become 0. Only I have to calculate for this up and down. So that is what it is done here. So in order to calculate the closed loop integration of magnetic field along this particular, so I have to take a small dl. So dl, we can easily say that it is for this particular direction, it is dx. For this particular direction, this is dz. So you can see that. So we have z component, x component, and z component, x component, and the corresponding directions. So one is along this particular direction, along this direction, this direction, this direction. Like that, it is taken 4 4 parts are there, 4 sections are there, we have integrated it. Now, obviously, we know that there is no z component, only x component alone available. And we are going to say that when you integrate this dx, you will get b. When you integrate this dz, you will get a. That's all. So we can easily substitute that. You will get 2 times of b will come because this 2 integrations. This integration plus this integration. So altogether, you are going to get 2 times of hb. And this, then we can say that which supposed to be equal to the total current according to Ampere's law. So if we know that 2 H naught B equal to the enclosed current I, here it should be K. I'm sorry, this is supposed to be K. K also in the Y direction. We should remember that. Then we can easily say that H naught equal to Ky by 2B. So if we say that the B is unit value, then Ky by 2. So we can easily calculate the magnetic field in both the both up and down. You can easily calculate that. Since the B is a relative term, at any particular point, we are going to get the same magnetic field. So this is what we can understand out of the given structure. I'm sorry, I have done a mistake. Okay, so this is the total magnetic field taken out of the loop. Now we have to calculate the current with respect to the Ky. Okay, so the total current, how much current will flow through this line? Through this line, how much current will flow? This is the B value. So simply we can say that it is B into Ky. So this is the total amount of current. So the current is nothing but B into Ky. So I am going to put this B here, both cancel. So I will get K by 2. Okay, so this is the answer. Now we are going to substitute this H naught here in this 2 point. If you substitute, this is the answer. So there are 2 possible magnetic fields for a infinite sheet. One is up and down, and at any particular height, you will get that. So if you take a sheet, then at any particular point, it may be at any height, then the magnetic field will be same strength. So that is the interesting point. And if you notice the similarity between the electric and magnetic field, it is very much, you will get the same behavior. So here also you will get the same. If you take an infinite line charge, you will get very similar type. There actually epsilon naught will come. Here the epsilon naught is available. That is a minor difference. And in case of this also, you will get the very similar expression. So you have any doubt, you can ask me. I will help you out. And this particular problem is a bit lengthy problem, but I'm not going to tell the entire derivation. You can learn by yourself, but let me summarize that. So what we have taken is we are going to calculate the magnetic field for a coaxial transmission line. So what is coaxial transmission line is nothing but there is a 2 coaxial cylinders which are having same axis. Okay, so this coaxial transmission line has 2 things. One is the inside conductor and the outside conductor. The inside conductor often referred as simply conductor, and this always be assumed as positive. Okay, which means that let's say the current is going along this particular direction. Let's say this is Z direction. So along the Z direction, it is moving, and this will be connected to positive of the source. Let's say this is the current source, or yeah, we have a current source. So if this is actually going in this particular direction, obviously the current which is going in the outer conductor will be always in the opposite direction. So how to define this in a cross-sectional view? So that is what you could see that. So for this particular structure, people always say that the current with like this, which means it is going inside the structure. Okay, or you can draw opposite way. So you can draw here cross mark. then obviously the outer will be just opposite of that. So this is the very important thing. So there are two different current flows we supposed to account for a transition for this particular transition line. So whenever you calculate the magnetic field from the center, when you keep on go outward direction up to this particular point, you got this inward direction. Then up to here also it is inward direction. Then after this outward direction. So this is the very interesting part. There are, we can say that four possible magnetic fields will be there. That is, one is inside this conductor, then outside the conductor one, and let me say this is actually one, this is two, then this is H3, then H4. And this H4 is completely independent of this interior structure, because this interior structure cannot give any current to this, because this current will be blocked here. This magnetic field will be blocked up to that. So H1 and H2 depends on the conductor one. Let me write it as a C1. And H3 and H4 going to be due to this conductor 2. Conductor 1 has, let's say if the current is I, for this the current is minus I. So this is the little bit crucial part. And the next very important thing for this cylindrical coordinate system, we can easily say that we can follow cylindrical coordinate system. Next thing, how to draw the Amperian path. Okay, so the Amperian path I already told, it's supposed to collect all the magnetic fields, okay, of the at that with respect to the particular point. So in order to do that, and it is a line vector, so and it is an infinite line, okay. So this is an infinite line along the z direction. So in order to collect all this structure, it is better to draw the circle. So at any particular point, we can follow the circle. So if our particular point P is here, 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 anywhere else, we need not worry. We can simply draw the circle as the Amperian path. So once this circle is drawn, then depends on the radius of the circle. So for this Amperian path, radius is less than A. And for this, it is more than A. And for this, it is more than B. And after that, it is still greater than B. So in this four different cases, we have to place this Amperian path and we have to collect the magnetic field. So that is what it is described here. So for the region up to A, then for the region up to B, then the region beyond B, how the magnetic field will be available. You need not to worry because it is an infinite line. For infinite line, we already have the electric magnetic field. The only thing we supposed to have the difference is the total current I. Because up to this, the current will keep on increase as radius increases. But after this, the current will be same, but the magnetic field will be different. And after from this case, opposite current will come and up to this one type and after that. So if this thickness is T, then B to B case. So that is what it is described over here. I recommend you to study this study Q book for this particular problem. And so you can expect some few 5-mark question or 3 or even 4-mark question or something in that size of question out of this particular numerical problem. Since it is open book test, you are simply going to refer that. But in order to apply this theory, you should know this all 4 magnetic fields. So I believe you have learned. So these are the 4 magnetic field components will be available inside and outside the structure. In the outside, there is no magnetic field because this, according to the right-hand rule, the magnetic field will be available in the clockwise direction. So in that case, it will be available only inside. Outside, it will not be available. So that is a very interesting part of this this coaxial cable. So it is perfect that if you send some information, through this is, let's say this is the modulated information, and this modulated information is traveling inside that. And outside that, there is no field component, no electric field, no magnetic field. So nobody cannot tap the information at this particular point. And if they try to tap it, how they can do? They have to break it. So if they break this shell and they try to put a wire inside that, then this entire shell got collapsed. So obviously these two components will not be available. If these two components are not available, the entire structure will not be a coaxial cable, and hence no flow of uh, no flow of signal. So let's say we break at this particular point, then after this signal will not flow. That is a very interesting part in the transmission line theory. And another interesting theory is, by applying this transmission line theory, at which particular point somebody broke it, we can even find that. Okay, and we can directly go to this place and we have to cut this and we have to rearrange this. That's all. Okay, so nowadays actually such a meter is available. Even you can see that some telephone exchange people, if you have noticed in your childhood times, now no people are available because all of you are using wireless mobile phones. But in at least 10 years before itself, you could notice that everywhere was exchange will be there. And if phone is not working, this person will come with the meter. They will simply connect the meter, they will touch some buttons, and it will tell at what particular distance the breakage is. Then they will go to the breakage point, then they will solve the problem. Any of you have noticed such people near to your home, or in your home itself some problem has come like that?
No, sir.
You are very unfortunate. Okay. So that is why actually even I asked some of the earlier batch student, do you know who is Graham Bell? They simply do not know, because even though he is the inventor of telephone, but nobody knows about that. But everyone knows about who is that? The CEO of Apple. Uh, in fact, he is not the inventor of phone or anything else. He is the inventor, we can say, that touch phones. That's all. So the important thing in case of the application of Biot-Savart law, we supposed to uh, clearly define the small magnetic field, and we have to calculate this dl and r vector. Simply by cross product of that, more you will get the answer. But in case of Ampere's law, you're supposed to know how to draw this closed path. That is the very important thing. Okay. Then only you can collect all the magnetic fields, and we can calculate the total current I. So it is a kind of a reverse problem with respect to the Biot-Savart law. So this drawing Amperian path is very important. So whenever your question is asked to you, whenever you're writing the exam, and whenever the problem told to use the Ampere's law, you're supposed to use the Ampere's law. So for this, the very first step is you have to draw the structure. So here it is an infinite line. So in the question, nobody will not show this type of figure or anything. You have to do it by yourself. So let's say there is calculate the magnetic field due to a loop. So this is the loop, circular loop. Okay. Then axis you are drawing, and it is carrying a current I. Now I have to calculate the magnetic field due to this using the Ampere's law. So I have to ask my question, how this so-called the magnetic field will be. So the magnetic field, we know that according to the right hand rule, it will be just around that. So it is going to be just around like this. So it is going to be just like this. It is going to be just around. Okay, this is going to be the magnetic field. So if I take a small portion, and with respect to that, we can easily calculate the magnetic field. Then we can apply over the case and we can calculate that. So here also the same current is going to flow. Here also the same current is going to flow. So at a small particular point, if you take it, you will get the answer. So the answer for the this particular question is, we are going to take a small current region, and this we are going to assume as a kind of a straight line. So that straight line can be here in this a finite line, we can say. Then we can calculate the magnetic field out of that. Then we can say that it is the same current is going to flow everywhere, like that also you can argue. So for this, you have to draw the Amperian path. This Amperian path will be nothing but a circle here. In that way also you can easily do that. So for a given structure, if you know the current, we can calculate the magnetic field. Otherwise, if you know the magnetic field, if you can sense the magnetic field using some apparatus, then we can use the Ampere's law to calculate the current going in. So this is how the uh, most of the people actually, you know that there are many electrical cables are going just above our head, at least at 20. So you could notice that some um, like this shapes might be there, and we are almost this much size, and cables will be running on this. Okay, so how we can say that the current is flowing or not? Okay, the very easiest answer is according to the laws, according to Ampere's law, the current is actually flowing around this direction. Now I am going to keep a apparatus here. This apparatus will collect the magnetic field, and this magnetic field, using this, I can easily say what is this distance, and by this I can calculate the current, amount of current, in what direction it is going. Everything we can find. So that is the, and this is how actually we can use this use this particular laws. There are multiple ways we can use that. Even to construct a inductor. So you already know about what is inductor. Inductor is nothing but helical structure, and then it is having magnetic field out of that. So it has north and south pole. And if it is a transformer, they will be linking each other. So how to construct this? So, and this, how much magnetic field is going from one one so-called one coil to another coil, that decides it. So by means of number of turns, we can calculate it, and therefore you can calculate the current I. So even very high voltage is coming to your home, 230 volt, your transformer can reduce to 20 volt, 10 volt, depends on that. So that is all interesting applications out of there with this Ampere's law. Here is a very simple problem that if you take two infinite sheets, okay, so there are two infinite sheets. One is placed on z equal to 0, another one is placed on z equal to 4, and they are carrying opposite currents of minus 10 amps per meter, and another one is 10 amps per meter in the same x-axis itself, but in the opposite direction. Okay. So then we have to calculate the magnetic field at these 2 points. The very first thing we have to do is we're supposed to draw proper diagram of these two infinite sheets. So at this z equal to infinite point, z equal to 0, let me put this. Okay, so this is going to be x-axis, this is going to be y-axis, this is going to be z-axis. So this is the z equal to 0 plane. X, this xy plane is the z. So here you have this z equal to 4. So now we have drawn two infinite sheets and they are carrying currents. So one is carrying plus I, another one is carrying minus I. And we have to calculate at this particular point. So we can easily see that 1, 1, and z equal to 1. The z equal to 1 is going to be somewhere else in this. Let's say this particular point. This is 1, 1, 1. Now these two infinite sheets will be having one distance here, another distance here, but anyhow, at any distance, we know that they are going to have the same magnetic field, k by 2. So it is going to give plus, and this is going to give minus. The very important question is, for this it is below, for this is above. For above it is positive, for this is below is negative. So obviously you will get opposite of that. By applying this two, you will see that at this particular point, the magnetic field due to this z equal to 0 plane, z equal to plane. So both are having same magnitude. In other words, they are going to add each other. You will get total magnetic field as a 10 AY along the y direction. That is very, very important. Ultimately, that is very important because when we take the cross product of the current direction and uh, the normal vector of the planes, then you will get the direction of the magnetic field. So that is going to be along this along this z direction, along the y direction. So one is along the minus y direction. This also along this the same direction it is available. So they are going to add each other. But if you see here, then both are actually in the opposite direction. In fact, they cancel each other. You will get zero. I think at this particular point you will get zero. You just cross check that. Okay, apply the same rule, the step-by-step manner. You should wonder that actually such a very advanced book. Substitution is really very excellent book. You people are studying only the preliminary or elementary part of that. It is also covering up many advanced applications. So in that case, you could see that Sadiq substituted all the values very gently. So you also do the same way. There won't be any mistake. But it is a time-consuming process. By practice, you can make it fast. You already know about that, how I told to attend the exam by considering Bruce Lee. The normal person and Bruce Lee both are going to do the same step. But the only intelligence of Bruce Lee is he can control his body in any mean such a way that at any fast he can do that. That's some difference between these two guys. So I just want you to transform to this. So for this, practice is very, very important. So take example, practice that such a way that your hand will cooperate you to write it much fast. The advantage of doing so is even there is some mistake during this calculation or something, then your fastness will cover up such a way that you can still get the correct, and you will get time to check all the answers also. There are some exercises I have given here. So I have completed Ampere's law and Biot-Savart law related things. Next we will go to magnetic flux in the next class onwards. Okay. So study well for quiz. Whenever you have a question, you can ask. You can share it with WhatsApp or Teams, and you can uh, don't call me because I'll be busy somewhere else. So the best